Hello students, welcome back to the series Coordination Chemistry. This is the fifth module of the series. Here we discuss different theories of coordination compounds. In the previous classes we have discussed, especially in the introductory part, we have discussed how coordination compounds, how the studies of coordination compounds were done, what was the preliminary studies done, who were the scientists who were contributing this to the coordination chemistry, etc. And so, I have in that class I have already told that it was Alfred Werner who is a pioneer in this field. He studied about different complexes, and so it is his theory that is the preliminary or primary theory in coordination compounds. So, we can discuss it as Werner's coordination theory, that is the first theory. It was in 1823 that Alfred Werner put forward his famous theory to describe the structure and formation of the coordination compounds, and also it was at his age of 26. And it is because of this theory that he got the Nobel Prize. Here are the important postulates of this Werner's coordination theory. Number one is central metal atom or atoms in coordination compounds show two types of valency. They are the primary and secondary valency. So, the first postulate is central metal atom. It exhibits two types of valency, that is primary valency and a secondary valency. The primary valency relates to the oxidation state and the secondary valency relates to the coordination number. And in the introductory part of this coordination chemistry, I have discussed, I have taught what is oxidation number, what is coordination number, etc. So, primary valency will be relating to the oxidation state, secondary valency will be relating to the coordination number. The number of secondary valencies is fixed for every metal atom. So, this secondary valency is fixed for every metal atom, and that it means that that secondary valency is relating to the coordination number. So, we can say that coordination number is fixed in a complex. And the metal tries to satisfy both its primary and secondary valencies, that is the central metal atom tries to satisfy both the primary and secondary valencies. A negative ion satisfies the primary valency. On the other hand, the negative ion or neutral molecules satisfies the secondary valencies. So, primary valency will be satisfied by the negative ions and secondary valencies will be satisfied by negative ions or neutral molecules. The secondary valencies point towards a fixed position in space. That is the reason behind the definite geometry of a coordination compound. Since the secondary valencies are oriented in space to fixed positions, that will determine the shape or geometry of the coordination compound. Since if the secondary valency, we know that the coordination number in coordination chemistry, we usually deal with the coordination number 4 and 6. If the second, the coordination number is related to secondary valency, or secondary valency is all about coordination number, and if it is the coordination number or secondary valency is 6, that will be arranged octahedrally. The ligands will be arranged octahedrally around the central metal atom. If it is 4, it can be either tetrahedral or it can be square planar. Two possibilities are there for coordination number or secondary valency 4. Therefore, we see that the secondary valencies determine the stereochemistry of the complex. So, the geometry of the complex is merely depending upon the secondary valencies. On the other hand, the primary valencies are non-directional. So, we can conclude that primary valencies are non-directional and secondary valencies are directional. It determines, secondary valency determine the shape or geometry of the complex. And now this Alfred Werner studied mainly, he studied chloramine cobalt 3 complexes. His studies was mainly on these complexes. In these complexes, cobalt has a primary valency of 3, means they are non-directional. Primary valency of 3 and secondary valency of 6. first complex which he studied was COCl3.6NH3, COCl3 6NH3. So, the coordination number in cobalt is 6, 6 is the coordination number, and we have 6 ammonia molecules. You can see that 6 ammonia molecules are there. So, this 6 ammonia molecule satisfies the coordination number of this complex, and this chloride ion Cl minus ion satisfies the primary valency, and they are non-directional also. This ammonia molecules will be satisfying the secondary valency, and they are directional. And how many chloride ions are precipitated? When he studied, he saw that the chloride ions precipitated with silver nitrate is, in this case it is 3 chloride ions were precipitated. So, the total number of ions precipitated was 4 means 3 chloride ions and 1 the complex ion. In this complex, while studying this complex, he saw that 3 chloride ions were precipitated on the addition of silver nitrate, and 1 complex ion was there. It is not having any chloride ion, so it will not give precipitate. On the whole, 4 ions will be there, 3 will be precipitated on the addition of silver nitrate. So, the structure he deduced was, it is like this: CONH3 6 times Cl3. Since these 3 Cl, they will be precipitated by the addition of silver nitrate as silver chloride. We know that it is a white precipitate. AgCl is a white precipitate, and he saw that there are 3 chloride ions and 1 complex ion. So, the structure deduced was like this. You can see the structure there. See this, in this structure he represented in different, one you can see this is a solid line. Solid lines are there and dotted lines are there, and the secondary valencies was represented by the solid line. So, how many solid lines are there? There are 6 solid lines, 1, 2, 3, 4, 5, 6 solid lines. You know that 6 is a coordination number, 6 ammonia molecules satisfy the secondary valencies, and 3 dashed lines or dotted lines are there. They show the primary valency, they are the primary valency, they are non-directional, but these are directional, they will be oriented in the fixed positions, and that determines the geometry of the complex. Number of chloride ion precipitated is 3 and total number of ion is 4. Now, the second complex is COCl3 5NH3. Here also the coordination number of cobalt is 6, but you can see only 5 ammonia molecules are there, and it was seen that the chloride ions precipitated here on the addition of silver nitrate was 2. On the addition of silver nitrate, only 2 chloride ions were precipitated, and also you have only 5 ammonia molecules. So, it was deduced that the structure will be like this. The structure he deduced was like this. In this complex, you can see that the only 2 chloride ions are there outside the coordination sphere, and these 2 chloride ions were precipitated by the addition of silver nitrate, and one become inside the coordination sphere. It merely acts as the ligands actually. So, it will not be precipitated in the solution. See the structure, you can see that 5 plus 1, 5 ammonia molecules acting as a secondary valency, and they are represented as a solid line 1, 2, 3, 4 and 5, and 2 chloride ions are representing the primary valency. So, they are represented as the dotted line, but 1 chloride ion, you can see that it is there are both lines, that is a solid line is there and a dotted line, both are present with 1 chloride molecule or chloride ion, because this chloride ion acts, it is having a dual nature. What is dual nature? 2 natures at the time, that is it is acting as a primary valency as well as a secondary valency. That is why a solid line and a dotted line is there. So, you can see number of chloride ions precipitated in this case is 2. Which are the chloride ions? This chloride ion and this chloride ion. 2 chloride ions will be precipitated by the addition of silver nitrate, but this chloride ion will not be precipitated because it acts as secondary valency also. And now the third complex is for COCl3 4NH3. In this complex, two Cl minus ions shows the dual nature, that is both primary valency, both as a primary valency and a secondary valency. How many chloride ions are acting dual nature, are taking the dual nature? 2 chloride ions. It was found that this complex exists in two forms. This same complex exists in two forms. One is having a green and another green color and another is having a yellow color. So, the type of isomers are expressed. Isomers are shown by this complex. One is a cis isomer, another is a trans isomer. Thus, the two forms which he studied, COCl3 4NH3 are this trans CO NH3 4 times Cl2 Cl and cis CO NH3 4 times Cl2 Cl. How it becomes cis? When this chloride ion, when this chloride ion, both the chloride ions are adjacent to the each other, it is called cis. If they are in the opposite direction, it is trans. One is having a green color, another is having a yellow color. And you can represent the structure like this. The structure he represented was like this. How many ammonia molecules are there? 4 ammonia molecules. They are merely acting as the secondary valencies only. That is why it is represented by the solid lines 1, 2, 3 and 4. And how many chloride ions are there outside the coordination sphere or are acting as a primary valency? Only 1. That is why a dotted line for this single chloride ion. And you can see 2 chloride ions with the dual nature, that is 1 and 2. They are acting as a primary as well as secondary valency. So, number of chloride ions precipitated with the silver nitrate will be, it was 1 and the total number of ions furnished was 2, that is 1 chloride ion and the whole complex ion. How it is? This is one complex ion and another chloride ion. 2 ions will be furnished in the solution. And this is how he studied about the complexes, several complexes. And this, you know that this is a preliminary or very primitive theory. It was the first attempt of explaining the coordination compounds. So, there are several merits as well as demerits for this theory. We can first go through the merits of this Werner's coordination theory. It helps to predict the exact molecular formula of the complexes. Exact molecular formula could be explained by this theory. The structure of 4 coordinated and 6 coordinated complexes could be predicted. You have seen that 4 coordinated complexes and 6 coordinated. 4 coordinated may be either tetrahedral or a square planar and 6 coordinated may be octahedral complexes that he could predict. It could predict the difference in behavior of different complexes of the same metal ion or same ligand. You have seen that same metal ion and same ligand will be showing different complexes, will be having different complexes will be formed by the same metal ion and same ligand. It could predict and explain isomerism also. You have seen that cis and trans isomer in the third complex, the COCl3 4 times NH3. It showed that 2 types of complexes, that is cis form and the trans form. When the 2 chloride ions are in the adjacent position, it was a cis isomer, and when it comes in the opposite direction, it is a trans isomer. So, the isomerism could be easily explained by this theory. And now, we have several demerits for this theory. It could not explain the nature of bonding within the coordination sphere. See, he could see only what are the ions precipitated, what are the secondary valencies coming. All those things were explained by this Alfred Werner, but he could not explain the nature of bonding between the metal atom and the ligand. So, nature of bonding was very, it was not at all discussed by this Alfred Werner. And he could not predict the preferences of 4 coordinated or 6 coordinated complexes. He could not able to explain the which all complexes will form 4 coordinated or which all complexes will form 6 coordinated complex. And also he fails to explain the actual geometry of the complexes, whether for example in the case of a 4 coordinated complex, whether it will form a tetrahedral complex or a square planar complex. all those things could not be correctly predicted by this Alfred Werner. And next was spectral or magnetic properties were not at all explained by this theory. No data about, it could not explain the magnetic or spectral properties of the complexes. And altogether there was no theoretical justification for the theory. Since it is a very primitive theory, no theoretical explanation was given by this theory. These are the merits of demerits of Werner's coordination theory. And now coming to the next attempt to explain the theories of coordination, to explain the coordination compound. The second one is Sidgwick's concept of coordination. It is related to the EAN rule. And what is EAN? EAN means effective atomic number rule. It will be discussed in the coming slides. This theory is merely based on the Lewis concept of covalent bond between two atoms in a molecule. You may be familiar with the different concepts of bonding, that is Lewis concept. What is Lewis concept? Lewis concept is merely discussing about the electron donor, electron pair acceptor, like that. Some atoms are electron pair donors, some atoms are electron pair acceptors. So, that type of explanation is given by the Sidgwick concept. Here the coordinate bond is formed between the central metal atom and the ligands. There is a coordinate bond formation between the central metal atom and ligands. And this bond, this coordinate bond is also called as dative bond or semi-polar bond. So, coordinate bond is otherwise called as dative bond or semi-polar bond. And here the ligands donate electrons. Ligands will be donating electrons to the central metal atom. So, ligands will be electron donors and central metal atom will be electron acceptors. And vacant orbital of the central metal atom accepts this electrons. Ligands will be donating a pair of electrons and they are called as electron donors, and central metal atom will be the electron acceptor. And for accepting this electrons, vacant orbitals should be there in the central metal atom. And now, this vacant orbital of the central metal atom, when accepts the electrons, they are termed as acceptors. And the bond between a donor and acceptor, see there is a bond with we are explaining the bond between central metal atom and the ligand. So, the bond formation between metal and the ligands, that is what Sidgwick is considering here. So, the bond between donor and the acceptor is called the coordinate bond, or it is dative bond, or otherwise called as semi-polar bond. And the number of coordinate bond formed, it depends on the number of vacant orbitals of suitable energy in the central metal atom. And now, it can be represented simply as like this. See the example, see there is a complex, you can see the cobalt is a central metal atom and 6 ammonia ligands are there outside the central metal atom, and you can see an arrow from each ligand. From each ammonia ligand there is an arrow which shows that ammonia molecules are donating electrons to central metal atom, and this metal is accepting this electron, represented by the arrow starting from the donor pointing towards the acceptor. Metal is a acceptor, ligand is a donor. So, it is L to M, ligand to metal, electrons are being donated. And now, we have told that Sidgwick concept is based on the EAN rule. What is EAN? Effective atomic number. Then what is effective atomic number? It states that, the rule states that thermodynamically stable transition metal compounds contain 18 valence electrons comprising of the metal d electrons plus the electrons supplied by the metal bound electrons. That is, it can be stated, or it can be described as effective atomic number is the summation of the electrons which are inside the metal plus electrons gained by the metal through ligands. So, on total you can say that effective atomic number. Okay. So, effective atomic number rule can be stated as thermodynamically stable transition metal complexes or compounds contain 18 valence electron comprising of metal d electrons plus electrons supplied by the metal bound ligands, and that should be summation of the electrons in metal and ligands, and the electrons which are gained from the ligands should be 18. On total you should have 18 electrons. When you have the 18 electrons, that complex or that coordination compound is very stable. That is the point. It is also called as 18 electron rule or noble gas rule. You may be familiar with the noble gases. They are exceptionally stable, inert gases. They are also called as inert gases. Why they are called as inert gases? Because very stability, because of their high stability. And the counting of this electrons, how to count the electrons? Counting of this 18 valence electrons in transition metal complexes may be obtained by following either of the methods. That is, you can actually follow ionic method, and the second method is a neutral atom method. Neutral atom method or ionic method could be used. And you can see in the coming slides you can work out the problems. Now, the neutral atom, in the neutral atom method, the metal is taken as is in a zero oxidation state. You are considering metal in a zero oxidation state. And now, in the oxidation state method, we have to consider, first we have to arrive at the oxidation state of the central metal atom. First you have to understand the oxidation state of the central metal atom, and you know that how to find out the oxidation state. I have already taught in the previous classes how to find the oxidation state. And firstly you have to arrive at the oxidation state by considering number of anionic ligands present and the overall charge of the complexes. All these things are discussed previously. And now we are going to the steps of the electron count. First, determine the oxidation state of the transition metal and the resulting d electron count. First we have to find the oxidation state and finally arrive at the d electron, how many d electrons are there, and identify. In that, first we have to identify any overall charges on the molecular complex, and next identify the charge of each ligand. And next, what is the next step is determine the number of electrons from each ligand that are donated to the metal center. So, first step is to find out the oxidation state of the central metal atom. From that you will get the idea how many electrons are there in the central metal atom. Second procedure is to find out how many ligands are there in the complex and how many electrons are being donated by the ligands to the central metal atom. And now, by understanding these two, you can just add these electrons and to get the effective atomic number. And now you can explain another example. FeNH3 6 times 2 plus. The oxidation state of iron, you can we have already studied how to calculate it. The oxidation state of iron is found to be +2. So, Fe 2 plus state, and you know that in this case you can actually count the electrons by using this method also. See, the atomic number of iron is 26, you know that the atomic number is 26. If iron is in the Fe is in the +2 oxidation state, how many electrons are given by iron? 2 electrons are given. So, from 26 2 electrons are gone, how many electrons are there? Now, it is 24. And how many ammonia molecules are there? 6 ammonia molecules. All ammonia molecules are, ammonia ligand is a monodentate ligand, will be donating 2 electrons. So, EAN, how can we calculate? You can actually sum up this. From the iron it is 24, Fe2 plus is 26 is Fe. Fe2 plus will be 24, 24 plus 6 into 2, 6 means 6 ammonia molecules are there, 6 into 2, so 12, 24 plus 12 it is 36. 36 is the atomic number of krypton, argon, it is krypton, argon is 18. It is atomic number krypton, since it is atomic number of, since it is the atomic number of krypton, krypton, it is a noble gas. So, it is exceptionally stable. So, the compound, the complex which we discussed is exceptionally stable, that is effective atomic number rule. Now, these are some exceptions are there for this effective atomic number rule. See the complex CuNH3 4 times 2 plus. The complex is having the central metal atom is copper. Copper is in the +2 oxidation state. Copper, it is having an atomic number is 29. Copper is atomic number is 29. And for Cu2 plus, it will be 2 electrons are gone. So, 27 electrons. And how many ligands are there? 4 ammonia. So, 4 into 2. Each ligand will be giving 2 electrons. So, 4 into 2, 8 electrons. So, you can just count 27 plus 8 electrons from the ligands, 27 plus 8, 35 electrons. You know that 36 is the noble gas configuration, but 35 is not noble gas configuration, but still the complex is very stable. So, it is an example for EAN, example for exception for EAN rule. Although the complex is very stable, it is not having the effective atomic number of that of noble gases. And now, other examples are also there. Chromium complex, this chromium complex, in this complex chromium is in the +3 oxidation state, Cr3 plus means it is 21 electrons, because chromium atomic number is 24, 24 minus 3 we have 21, 21 plus how many ligands? 6 ammonia. So, 6 into 2, 12 electrons. So, on total you have 21 plus 12, that is 33. You don't get the atomic number of a noble gas, but still the complex is highly stable. This is another example for exception of effective atomic number rule. And here also this theory was also having many demerits. Many demerits were there. Many demerits means the main thing is explained here. First, many complexes are quite stable, but even though they does not obey effective atomic number rule. You have seen the examples. And second one is, in this concept, according to Sidgwick's concept, this ligands are donating electrons to the central metal atom, and the central metal atom is accepting all these electrons. So, electron donors and electron pair acceptors concept is there. So, if electrons are being donated by the central metal atom, there will be an accumulation of electrons in the central metal atom. There is a possibility which leads to the instability of the complex. That is the demerit of this Sidgwick theory. So, these are the main demerits of Sidgwick's theory. And now, this is all about the two preliminary theories in coordination compounds. In this in this class, we have studied two theories. First one was the preliminary theory, that is Werner's coordination theory, and second is a Sidgwick concept. And I think it is clear, effective atomic number rule, everything is clear. And now, in the next module, we will be discussing about the coming theories, that is the advanced theories in coordination compounds. And the first advanced theory is, of course, it is valence bond theory, that will be discussed in the coming class. Thank you all for watching this video. Thank you.